Okay, hi guys, this is Chem 100, the support notes part one, the support notes number one, and this is part two of the support notes. And what we're defining here is something called partial pressure of a substance. And so I want to just start with a really quick little side note here that we have three states of matter, and there's actually four, but we're only going to talk about three. We have solids, and an example would be ice, if we're talking about water. Liquid would be like drinking water, and then gas would be associated closely with the concept of steam or water vapor. So that would be water in all three different states of matter. Okay, so we're going to focus on the gases here. And I just gave a couple of really quick statements. The first one is that gases are highly energetic particles moving very fast, running into each other and the walls of their container. And I always thought of gas particles kind of like people in a mosh pit. And hopefully you guys know what a mosh pit is. If not, you can Google one. But they're, people crashing around into each other. And if the people are like the particles of gas, then, they're running into each other and running into the walls of their container, which would be like the outside of the mosh pit. Okay, every time a gas particle hits the wall of the container, it exerts a small force. And all the particles together make up a larger force. And if we look at that force that's exerted and divide it by the area that it's exerted in, we get this idea, or we get this variable called pressure. So pressure is a trait that's associated with gases. So we have pressure, volume, temperature, and moles when we talk about gases. And so there is a definition for pressure. It's just the force divided by the area. And we're going to take a little step back and talk about a couple of the other variables that are associated with gases. So the other variables with gases, and this pressure is denoted with a capital P. I forgot to say that. So other variables with gases. We have pressure, we have volume, which is denoted with a V, and that's in liters. So how much space, three-dimensional space, does the gas take up? We have temperature, and that is denoted with a capital T. And with temperature, we use the Kelvin scale. So that would be Kelvin is equal to degrees Celsius plus 273. And I can go into that a little bit more later on. But whenever you do any calculation for a gas, you always use the Kelvin scale for the temperature. So far we've got pressure, volume, temperature. And our last one is moles of gas. And that's just a measure of how many particles there are. And moles is denoted with the lowercase little cursive n. So this is a measure of the number of particles in the sample. Okay, so now that brings us to our secret equation that I want to share with you. An equation that relates all of these variables together: pressure, volume, temperature, and moles. I'm going to put in like this so it matches the other ones. And that is called the ideal gas law. And the ideal gas law goes like this: pressure times volume is equal to moles times R times T. And I'm just going to break that down for you for each of those variables. Obviously, P is pressure, and we need that to be in atmospheres. Those are the units. V is volume, and that's in liters. N is moles of the substance. We'll get back to R. And T, of course, is temperature in Kelvin. V-I-N. Okay, so the ideal gas law says that the pressure times the volume is equal to the moles of the gas in the sample times this number R times T. So the R value is what makes this into an equivalence. It makes pressure times volume equal to N times T, but we got to multiply by this factor R. And when we're using liters, atmospheres, moles, and Kelvin, R has a value of 0.0821. Okay, and that's a constant number. As long as you're using liters, atmospheres, moles, Kelvin. Okay, so in this type of formula, we could solve for any one of these four variables that are given. R is not a variable, it's a constant number, and we can do all kinds of fun stuff with it. But what we're concerned about is in a mixture of gases, which is what we often have in an equilibrium situation. So we can say in a mixture of gases, we can solve for the pressure coming from a specific gas. Only. Okay, and that would be the gas's partial pressure. And I was totally off there, sir. Let's get that back over and give you guys a minute to find what you needed. Sorry, I was totally off there. Okay, so in a mixture of gases, we can solve for partial pressure, and that's the pressure that's coming specifically from a given substance. Okay, so I'm just going to draw really quick. We could have a sample of gas A, if these are all gas A molecules, and then we could have a few gas B molecules in here. These are all bumping around in there, having their own little mosh pit. And we would know that total pressure is going to be equal to the sum of the partial pressures of each A and B. So we'd have partial pressure of A plus partial pressure of B. And that gives us a total pressure. So that's kind of one way to think of it. And the other way that you can find partial pressure is to use the ideal gas law. And so if we use the ideal gas law, we know that pressure times volume equals moles times R times T. Now, if I use moles of A, then this is the partial pressure for A. Sorry, that's really squished. I'm going to just rewrite this. This is partial pressure of A. Okay, so I'm going to do a really quick little example over here on the right. So partial pressure, if we have 2.6 grams of hydrogen mixed with 2.6 grams of nitrogen. What is the partial pressure of the N2 if temperature equals 25 degrees Celsius in a volume of 3 liters? Okay, so we got 2.6 grams of H2 mixed with 2.6 grams of N2. And we want to know what's the partial pressure of the N2 if temperature is equal to 25 degrees Celsius and it's in a volume of 3 liters. So we're going to move on to the next page here and do that problem. I'll keep it right here so that I can refer to it. Okay. So the first thing that we need to do is find out how many moles of N2 there are present in the mixture. So I'm going to say this is our example, and this is our example continued. Okay, and so what we're going to do is take the 2.6 grams of N2 and we're going to convert to moles. And the molar mass of N2 is 28.041 or 28.014. So I'll take 2.6 divide by 28.014 and I get 0.0928, and that's moles of N2. And I just learned my ideal gas law up here, PV equals nRT. I know the moles of the N2, I know the temperature, I know the volume, so I can easily solve for the partial pressure. So we're going to use PV equals nRT, remembering that the N is the moles of A. So we can put a little subscript here, P sub A, indicating that we're talking about, oh, sorry, not A, N2. The partial pressure of the N2 times the volume is equal to the moles of the N2 times R times T. So that makes our expression a little bit longer, but it won't be too difficult. The partial pressure of the N2 is what we're interested in. And we know our volume is 3 liters. And the moles we found just now to be 0.0928 moles. And the value of R is 0.0821. And the temperature, remember, has to be in Kelvin. So we take our degrees Celsius and add 273, which gives us 298 Kelvin. So we're going to do a little bit of baby algebra here. We're going to multiply 0.0928 times 0.0821 times 298 and divide by 3. And so our pressure, N2, comes out to be 0.757 atms. So that's in atmospheres. Okay, so so recording, sorry, I got totally off there. So anyway, this would be our partial pressure of the N2 if we solved using the ideal gas law. And I'm trying to think if I need to do anything else for those equilibrium notes. You got concentration, You've got partial pressure. I think that should be good. So, yeah, I think we're good. Okay.